an easy example, and let me solve these examples related with the open circuit and short circuit test. And let me first read carefully. A 200 kVA, that is the rated power of the machine. 480 volts, that is line-to-line voltage. It is rated. Such a machine is designed to operate such a voltage. Under such conditions, these machines will deliver such a power. It is the design value. That device can manage this easily at a rated value, at a nominal value. The frequency is 60 Hz. Take care, it is not 50. Machine has 4 poles. Double pole number, there are 2 pair of poles. Star connected, sometimes it is called as Y. It looks like star connection. Synchronous generator. Okay, that is a synchronous generator. Machine is operated as a generator with a rated field current of 5 amps. Was tested and following data was taken. Such a machine tested under 5 amps field current, and then here are the results, measurements. Here are the measurements. Okay, from open circuit test, terminal voltage is 540 volts at rated field current. Open circuit terminal voltage. Okay, here is something confusing. I will express later. Okay, from short circuit test, line current 300 amps at rated field current, 5 amps. From open circuit test, terminal voltage is 540 at field current, at rated field current. Rated field current is 5 amps. Okay, as you see, experiment is conducted under 5 amps, which is rated field current. All those 2 tests are conducted under such a field current. From DC test, I have previously explained here. From DC test, DC voltage of 10 volts applied the two-phase terminals. Just like we have done here. Two-phase terminals. Okay. 10 volts. Here it is 10 volts. And then a current of 25 amps was measured. Here is 25 amps. Okay. Now, as you see, you can calculate array from that DC test. Calculate the speed of rotation in RPM. That is very easy. And then calculate the generated EMF and equivalent circuit parameters, armature resistance, blah 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 blah. Okay, let's start somewhere. Let me change color and thickness. Okay, you should draw a diagram, draw a schematic diagram to understand what is happening. From open circuit test, terminal voltage 540 at field count. Machine is connected star. Here are windings inside the stator. It is connected star, and here are three-phase terminals. We defined UVW, and then here is excitation current. Here's a field point. You have applied 5 amps. Then in open circuit test, machine can generate 540 volts at 5 amperes field current. Tata, Houston. When here's 5 amps under open circuit test conditions, here you see you measure open circuit voltage. We want line 0. Line to line voltage, line. And 0 no load, means no load. It is 540 volts. Ladies and gentlemen, what is the voltage on one phase? One phase no load voltage is equal to 540 over root 3. That is the voltage. Let me calculate that by using my hand calculator. It is 311, let me say 11.8 volts. Okay, it is something like that. That is the single phase voltage. That is the voltage induced across one phase coil, or it is simply, remember, here is the EF, here are some impedance elements, and then here is terminal voltage of one phase. In case there is no load, in case there is no current, you see terminal voltage under no load condition is equal to induced EMF, field EMF in the machine. In fact, that guy is equal to EF. Houston, that is EF. And you can estimate what is happening inside the machine. Here is IF, here is EF, I mean open circuit test, and then here's a point. Just one point is given in this question. Here's 5 amps, and here is 311.8 volts. That is the just one of the point on no load curve. It would be something like that. I'm not sure whether there is a saturation or not. I don't know, but I know a certain point on these curve, and in fact it is not given here, but that point in fact must belong to unsaturated region. Unsaturated region, because if you force machine to a saturated region, the values will not represent linear region. For example, here you see such an open circuit test. Here's a linear region and then saturated region. Someone will give you some data taken here. IF versus EF. Those points are given. But you can calculate some impedance here, but that impedance not represent the linear region. Machine is generally operated in that linear region. General operation region. Because that is forced region, saturated region. So values taken in saturated region cannot represent the linear region. So please take care if you anytime will face such a condition. Please refer linear region. Choose values in linear region. And or even if it is not mentioned here, the point must be taken in linear region. We should accept that it belongs to linear region. Okay, we've got open circuit test for one phase right now. We have understand what is happening in the machine. That voltage belongs to line value, and then we have find out the single phase voltage, and we conclude that single phase voltage is equal to EF under no load condition, and it is a point on open circuit test. We just understand those kind of things happened. In the section B here, from short circuit test, line current 300 amps at rated field current. Okay, remember short circuit test. Here is field current, here is line current of one phase, single phase current, excuse me. And then again at rated field current, which is 5 amps, machine delivers 300 amps at a short circuit current. I1 short circuit, let's say I1 short circuit, that's better. Okay, and you know that this region is surely linear, because non-saturated region is much more further, because I assure you it belongs to linear region generally, because otherwise machine windings will be damaged. For example, you conduct a real short circuit on a system, there will be crazy currents, not 100 amps. There will be thousands of currents. For example, there will be 3000 amps. So I squared R, which is the core loss, copper loss in armature winding, will be crazy due to large short circuit current and square power of that current. So machine will burn out. It will be very dangerous, cannot be done, mustn't be done. So saturated region is somewhere here, at a very distance. So here's the point. Okay, now we are ready to make some calculations. From DC test, again, something must be interpreted. From DC test, here are the electric terminals, one phase. You apply 10 volts. You apply 10 volt DC. Here is a voltmeter showing 10 volt DC. Here's a ammeter, displays 25 amps, and you conduct experiment between two phase terminals. Here you say UVW, three phase terminals. You conduct that experiment between two phase terminals. Okay, it is easy. Here is array, here is excess, here is array, here is excess. But since you applied DC, there is no frequency in this case, Houston. So excess will be 0. So double array, which is total resistance around this loop, is equal to voltage applied over current drawn, which is equal to 10 over 25, 10 over 25 makes 0.4 ohms. Ladies and gentlemen, that was double array. You interpret from the figure. You should draw the figure. So array is simply 0.2 ohms. That is the armature winding resistance you have find out experimentally. Okay, now we have conducted the second part. In fact, calculated generated EMF, what's happening, and equivalent circuit parameters. Okay, we have just calculated one of the equivalent circuit parameter, which is array. We have just find out this. Calculate, let's do this. Calculate the speed of rotation in RPM. Ns is equal to 60 F over pole pair number. 60 times 60. Frequency was 60 Hertz. So 60 times 60 over pole pair number. There were two pair of poles. 2. So Ns is equal to 3600 over 2 makes 1800 RPM. That is the speed we have find out. It's okay. Now calculate the generated EMF. Here it is. We have already calculated. That is the generated EMF. 311. It is there. And then calculate generated EMF. We have already done this. Equivalent circuit parameters. We have calculated array. And now let's calculate synchronous reactance. First of all, let's calculate impedance. Impedance is equal to EF at 5 amps over short circuit current at 5 amps. They were 311.8 over here were 300 amps. It makes, let me calculate it, 311.8 over 300 makes 1.39. That is the impedance. So reactance, synchronous reactance is equal to 1.39 squared minus the armature resistance, which is 0.2 squared, and then all in square root. Let me calculate. Minus 0.2 squared equal all in square root. It's I have calculated it by my hand calculator. I hope I done it right. 1.02 ohms. That is the excess. Let's check it out, the given results here. That is the speed we have already calculated here. That is the speed we have find out. Okay, and then here is EF 311.8. Here it is. We have drawn here. That's okay. And then Here's the impedance. It is here, and that guy. Let's check it out. 1 point. Yes, it is approximately, you see. You can round as 4. It is identical almost. Okay. From DC test, one of the resistance is 0.2. It is already here. And then resultant reactance, synchronous reactance, is here. Okay, here you see how can we combine those two experimental data to calculate equivalent circuit parameters.